The topic of relative velocity is kind of a standalone topic in this course. It's not that it's not important or not interesting, it's just that it doesn't come up very often in this course. What I'll do here is introduce you to this topic, point out some important things about it, and then we'll look at a problem or so. Let me first give you an example of where this concept, this idea of relative velocity can come up. Suppose you're driving down the road in a car. Okay, so here's the car. And you're inside the car driving right there. There's somebody in the back seat riding along with you. So here's your passenger in the back seat. Maybe somebody calls you up and asks you this very strange question. What is the velocity of the person in the back seat? You could look in your rearview mirror and notice that relative to you, the person in the back seat isn't moving at all. They're always, say, 3 feet straight behind you. So that position isn't changing at all. So you could certainly say the velocity of the person behind me is 0. They're not moving at all, and you would mean relative to me. On the other hand, if your car was going at 60 miles an hour down the road, you could also say that person is moving at 60 miles an hour. And in that case, what you would mean is they're moving at 60 miles an hour relative to somebody else standing on the side of the road watching this car pass by. So the velocity of an object always depends on who's observing the object. Velocity is the time derivative of a position vector, and that position vector goes from some origin to the object that's being tracked. If the origin changes, the velocity vector can change. And in particular, if one origin is moving relative to some other origin, you will get 2 different velocity vectors. So let me set this thing up and show you how we account for that change in coordinate systems, that change in origin. I'm going to draw here 2 coordinate systems. I'm going to call this one a stationary one, so I'm going to call it S. And this would be like the person standing on the side of the road. And here's another one. I'm going to call it M for moving. And you can imagine this is the moving coordinate system like the car that was driving down the road. So those are our 2 coordinate systems. And now we need an object that's going to be observed, that we're going to measure the velocity of. So I'll draw that here, and I'll call it O. That's the object. Okay, so we would like to know the velocity of this object O. And in particular, we would like to know how the velocity measured in this stationary frame relates to the velocity measured in the moving frame. The way to get this is to draw some position vectors and take their time derivative, because that's what velocity means. So let me draw a couple of position vectors here. I'll draw them in different colors. Here comes one in orange. And it is the position. We're going to have some notation here to keep track of what we're looking at. This is the position of O with respect to the stationary frame. So notice my subscripts here. This is the position vector, the object that's being tracked, and the reference frame that's being tracked from. So this is the position of the object as measured, as observed from the stationary reference frame. Okay, now let's draw the other one. From the moving frame, we have this position vector. And that is going to be, I'm going to put it over here, position of O relative to the moving frame. There's one more vector we can draw. If we want to relate the velocity between these 2 frames, we need to know the position of those 2 frames, and in particular, in a minute, how that position is changing. So I also need to draw this vector from the stationary frame to the moving frame. That is the position of the moving frame relative to the stationary frame. Okay, so I have 3 vectors there. Two of them show me the position of the object relative to the two different frames, and the third one shows me the relative position of the two frames. Think again of the car and the person standing on the ground. What I want to do now is write the vector relation among these three position vectors. And notice that there is a vector addition that we can draw. This vector plus that vector equals this vector. So apparently, the position of object O relative to the stationary frame equals the position of object O relative to the moving frame plus the position of the moving frame relative to the stationary frame. Before I go on, I want to note one thing. I could take any of these vectors and reverse the subscript, and that would introduce a negative sign. If, for instance, I took this vector right here and drew it in the opposite direction, so that instead of ROM, I had RMO, the position of the moving frame relative to the object, that vector would go in the opposite direction, and it would be minus the original vector. And all of what we're doing here, if you reverse the order of these subscripts, you introduce a negative sign because it turns the vector around backwards. All right, now come back over here. This is the expression that relates the positions. But what we want to know is how the velocities relate. If you have an expression for positions and you want to know about velocities, what you need to do is take the derivative, the time derivative, because velocity is the time derivative of position. So let's take d by dt of every term in this expression. And what it tells me is the velocity of object O as measured in the stationary frame equals the velocity of object O as measured in the moving frame plus the relative velocity between those two frames, the velocity of the moving frame relative to the stationary frame. And that's our velocity addition equation. This is our relative velocity equation. All of the problems in this section come down to writing the correct relative velocity equation and then solving this vector addition problem. So when you solve a problem here, the first thing you need to do is to identify the two reference frames and the object that's being tracked. When you find them, you want to construct this equation. And there's a couple ways of doing it. One way is to draw this picture each time, draw the position vectors, and then take the time derivative, positions turn into velocities. And that will work. Another way to do it is to notice the pattern in these subscripts. Here we have the velocity of the object, whatever it is that's being tracked, relative to the stationary frame. So OS. Notice the pattern that's going on here. I'm going to circle this. Here's an O right here. The first subscript on this side should also be an O. And then you have an S here. That's the second subscript on the left-hand side. That should be the last subscript on the right-hand side. And the other subscript in the middle should be the same. So O relative to S is O relative to M plus M relative to S. When you construct your velocity addition equation, if you've done it properly, this pattern will always be followed. Now sometimes we're told not the velocity of, for instance, M with respect to S, but S with respect to M. So you could rewrite this as the velocity of O with respect to S is velocity of O with respect to M minus velocity of S with respect to M, using this fact up here after taking the derivative. So depending on what you're told in a problem, you either write your equation this way or this way. Okay, so that's most of what we need to say here. I want to make one additional point. We went from the position to the relative velocity equation just by taking a time derivative. There's nothing stopping us from taking another time derivative and relating not only velocities, but accelerations also. Suppose I took another derivative. I took d by dt of this equation. then I would get the acceleration of object O relative to the stationary frame is the acceleration of object O relative to the moving frame plus the acceleration of the moving frame relative to the stationary frame. This equation we won't do anything with here, but it'll be of interest in the next chapter when we talk about forces. The forces acting on an object will be related to the accelerations. An important case is in what's called inertial reference frames that are not accelerating. And they're important because this acceleration is related to the force on the object. And it turns out to be inconvenient when we have apparent forces in one reference frame not equaling apparent forces in some other reference frame. The way you avoid that is to make sure that the two reference frames are not accelerating relative to each other. So if that term goes to 0, then we are in a so-called inertial reference frame, and forces in one reference frame will equal the forces in the other reference frame. So that'll come up a little bit in the next chapter, but here we're just going to focus on the velocity addition equation. There are a bunch of subscripts here, and I know this topic can be kind of confusing as you get into it, but if you work through a couple of problems, you'll start to see how they go. The key thing is to write this equation properly, to identify your reference frames carefully, to identify your object carefully, and then to work out what each of these vectors are so that you can solve the vector addition problem. Okay, let's look at a problem now.